In this lecture I would like to talk about the cross product. In the last one we talked about the dot product. Let's start with our two vectors v1 and v2. The cross product, it's defined as v1 cross v2, and in this case as a result we do not get a scalar, we get a vector. And how do we compute this product? Well, there is a rule, okay, which consists in calculating the determinant of a matrix. v1 cross v2 is given by the determinant of a matrix whose first row is given by the unit vectors of our orthogonal axes I, j and k. I is the unit vector along x, j is the unit vector along y, and k is the unit vector along z. And then in the second row we insert v1x, so the x component of the first vector. Then we have the second component v1y of the first vector, and then the third v1z. And here in the last row we have to insert v2x, v2y, v2z. And how do we compute this determinant? Well, the rule is the following. We expand it according to the first row. This is Laplace rule. We start from this point here. We erase the first row and the first column, and then take the determinant of this submatrix. And this is easy to do because we have to multiply this term by this term and then subtract this term multiplied by this one. So it's I multiplied by v1y v2z minus v1z times v2y. And then we have to expand according to the second unit vector, which is j, but in j we have to insert also a minus sign, so it's minus j times, we have to compute a determinant of a submatrix, and this submatrix is obtained by erasing the second column and the first row. So we have to multiply j by v1x times v2z minus v1z times v2x. So it's v1x times v2z minus v2x times v1z. And then we have the last term here, k. We have a plus k times this determinant obtained by erasing the first row and the last column. So it's k times v1x times v2y minus v1y times v2x. So it's v1x v2y minus v1y times v2x. And this is a definition, as I said. But we will use the definition to interpret geometrically this cross product, okay? And the first interpretation that we will give, we will do that in a few steps. We will show that v1 cross v2, the magnitude of this vector, because that's a vector, as you can see it has an x component because there is an I here, so it's a unit vector along x. This is the x component of the result. This is the y component of the result, with a minus sign because there is a minus here, and this is the z component of the result, so it's a vector. If we take the magnitude of this vector we get a scalar, and this scalar we can prove it to be equal to the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between the two vectors. So instead of the cosine we have the sine in the case of the cross product. So now it's up to us to show that this expression is equivalent to this one. Obviously we have to insert the magnitude here, we have to calculate the magnitude of this expression. Before doing that, I will also give you the definition in the case of just a 2D vector, because in this case we are considering 3D vectors, but I can compute the cross product also if the vectors are two-dimensional. In this case we just put in the first row v1x v1y, and in the second row the components of the second vector v2x v2y, and this is just equal to the determinant of this, so it's v1x v2y minus v1y times v2x. And remember, this must be a vector. This is multiplied by the unit vector along k, and I should put it here as well because we are on a plane. In this case we have x and y, and we should use the right hand rule to calculate the cross product. In particular, if this is v1 and this is v2, we move our hand from v1 to v2, and our thumb gives us the direction which the resulting vector goes along. So the cross product on a plane gives us a vector which is going outwards or inwards the plane, so it's perpendicular to the plane. That's for sure. And we can also obtain this from above, because we can just simply set, for instance, v1z and v2z equal to 0. And if you do so, you can see that this goes to 0, this goes to 0 because they are multiplied by v1z and v2z. This goes to 0, this goes to 0 because there is a v2z and v1z. And we are just left with this one. So the first definition, as you can see, reduces to this one if we have vectors which belong to a plane. But now we will prove the relation that I wrote down right here. So starting from the definitions, we want to prove this relation right here. And we will do that by using the vectors that I drew here on a plane, because it's easier, but the same result could be obtained by using this more tricky definition if the vectors do not lie on a plane but they lie in space. And never mind, because I can always find a plane over which those two vectors lie. Even if the vectors are not on a plane, I can draw a plane, and this plane can contain those two vectors. And then I can call that plane the xy plane. So I can always reduce myself to this kind of situation. So it's easier to prove it from here. And it's very similar to what we did in the last lecture. I can just rewrite v1x, v2y, v1y, and v2x in terms of their magnitude. So for instance, so this angle here is alpha, because it's the angle between the two vectors. I will call this beta. And then v1x will be equal to v1 times cosine beta, as you can see from here. This is v1x. v1 times cosine beta gives me v1x. v1y is equal to v1 sine beta, whereas v2x is equal to v2 cosine of alpha plus beta, because in this case we have to consider this entire angle here. And then we have v2y equal to v2 sine of alpha plus beta. And if I substitute these expressions in here, I get v1 cross v2 equal to, I can factor out the product v1 times v2, and then I have cosine beta, which I obtain from here, times sine of alpha plus beta, which comes from substituting, instead of v2y, we get v2y equals to v2 sine of alpha plus beta. So we insert this in there, and then we get this term. Then we have minus, very similarly, sine beta cosine of alpha plus beta. And you can see that this resembles the sign of the sum of two angles. Sine of gamma plus delta is equal to sine gamma cosine delta plus cosine gamma sine delta. And if we have a minus sign here, we have a minus sign here as well. So as you can see from this expression, this here is just gamma, whereas this is delta. So we have sine of alpha plus beta minus beta. So this is equal to the sine of alpha, which proves our interesting relation. And to conclude this lecture, also I will introduce to you the area of a parallelogram. In particular, if you want to compute the area of a parallelogram, which is something that we will use in some next lectures when we talk about the Jacobian and the transformation relating one set of variables to another one. If we want to compute the area of this parallelogram, which can be split into two different triangles, well, this is given by none other than, and in particular, this was the magnitude of the cross product. Otherwise, I would have simply put here the unit vector k. It doesn't really change anything. So I could either write it like this, or I can write it with the unit vector k. It doesn't really matter. So we have v1 cross v2, magnitude is equal to v1 v2 times sine of alpha. But v1 times v2 times sine of alpha is just the base of this triangle times its height. And base times height is twice the area of this triangle. So it's this area plus this area. And we get the area of a parallelogram. So that's why I introduced it here. So this is another geometric interpretation, and it's very important.